Okay, so in this second example, I just want you to think about the story of what's going on. If we were imagining that we were modeling a spring mass system, and then we're going to check this out. I want you to make a first guess as to like what you expect to see happen. So because it's second order and all of our coefficients are positive, it does model a spring mass system. This is undamped. So this is going to be in simple harmonic motion, just sines and cosines. And we start with an initial displacement. So it's just going to be, bobbing up and down and up and down. So we have an initial displacement of 1. This is going to be our maximum amplitude. Okay. All right. And it could just go on forever. Then at t equals 2 pi, we're going to apply an impulse. Okay. So we have our spring mass, bobbing up and down. At time 2 pi, we hit it with a hammer. And what I'd like you to just make a guess as to what you think will happen. We're going to be applying this force over a large force over a short time period. Okay, what do you think will happen to your solutions? For this, I would recommend that you bring out your formula sheet for the Laplace transform, just to have it at hand. And let's get started. Okay. So we're going to take the Laplace transform of both sides. We have s squared times y minus s times y at 0 minus y prime at 0 plus the Laplace transform of little y, which is just big Y, is equal to 4 times the Laplace transform of delta of 2 pi. So the delta function centered at 2 pi, and this is just e to the negative 2 pi s. All right, we're going to put in our initial conditions. So we had s squared y minus s plus y is 4 e to the negative 2 pi s. I'm going to move everything that doesn't have a y in it over to the other side. So s squared plus 1 times y is 4 e to the negative 2 pi s plus s. And then I'm going to divide over to solve for y. So y is 4 over s squared plus 1 e to the negative 2 pi s plus s over s squared plus 1. Okay. All right. And now we are ready to take some inverse Laplace transforms. Okay. So we have two terms. One of them is multiplied by this exponential. So that one will need some special treatment. This s over s squared plus 1 term, that's nice and easy. So I'm just going to write it down. This is cosine of t. That's our starting oscillation. Okay. And let's take a look at this other term. Okay, we're using the inverse Laplace transform of e to the negative as times f of s is ua of t f of t minus a. So what we're going to do is take the inverse Laplace transform of 4 over s squared plus 1. And that gives us little f of t. So that's 4 sine of t. Okay, so we have u2 pi of t, because our a here was 2 pi times 4 sine of t minus 2 pi. Lucky for us, sine of t minus 2 pi is the same thing as just sine of t, because it's periodic with period 2 pi. Okay, so we see first off, we have our cosine function up and down at 2 pi. When we are at this maximum displacement, we're applying an additional force. And so it's going to go further out. So if we were to write this with piecewise notation, at first we're just given cosine of t when t is less than 2 pi. But when t is bigger than 2 pi, we're going to look like cosine of t plus 4 sine of t when t is greater than 2 pi. And if we're curious like what the amplitude is, we've actually seen how to find that amplitude. This new amplitude, we just take the square root of the sum of the squares of those cosine and sine coefficients. So that's 1 squared plus 4 squared. So this new amplitude is square root of 17. And so after that one-time application of force, we are now forever onwards having amplitude square root of 17. Hey, great.